In Unit 17, we already talked about most of the characteristics of a wave, but there are a couple we left out. So we're going to quickly go through the ones that we already know, and then just add our new terms. Okay, so again, we say that we have this axis. We'll say that this is going to be the x-axis as a function of time. This is going to be the y-axis as a function of time, and so we have a wave that's propagating through the x-axis. Okay, so if we look at the distance from peak to peak, we call that lambda, where lambda we define as the wavelength. We know that we have, from these minimum positions, we have the amplitude, which is the distance above or below the point that we're oscillating around for an oscillator. But in general, for a wave, it's just the the height of the wave. Right. So A is going to be the amplitude. Okay. We can still also talk about the period, even though we can't really see the period on here, because the period would be a function of time, and so we would have to watch this wave move in time to be able to see what the period actually is. We still have a notion of the period. We can still say that the frequency is 1 over the period, and that the angular frequency is 2 pi over the period. Okay. Note that we also mentioned that we have this concept of the wave velocity. So that means if we take a point on the wave, it's going to be propagating with some velocity v, and we can say that the velocity is equal to the wavelength divided by the period, which is the same as saying the wavelength times the frequency. So here we define, so this is how we actually define the velocity of the wave. So it's going to be a product of its wavelength and its frequency. Okay? But there's actually one more characteristic. So remember when we talked about oscillating waves, we were using a function that looked like x of t equals a sine omega t minus phi, where phi is some phase. Okay, now we say, well, we have this wave that's propagating in the x direction. This is the y component, so we're going to say that y of t is some amplitude sine k times x minus omega t plus phi, and the pluses and minuses, it doesn't really make a difference. So phi is the phase of the wave. So in other words, we could be looking at, we might not have looked at this wave at time t equals 0. So we could have a wave that looks like this. And so in that case, notice that we have this difference here. This is called the phase. So this is what phi is. Okay, we have the angular frequency multiplied by time, not the regular frequency. And then we have this other factor here, k. We call this the wave number. And it's basically just that. It's telling us, each one of these waves has a different wave number, and it's telling us which wave we're actually on. And we define k as 2 pi divided by the wavelength. Okay, and so that's what this really does, is it tells us what number wave we're looking at. So by knowing the number of the wave and the frequency and the phase, that gives us everything that we need to know about how a wave looks like in time.